it from the Earth's core to the clouds, and that will become more apparent as you hear from our first speaker. But I want to just point out on the table, as you were coming into the venue here, we do have a brochure, which is our Science Cafe series. There are 4 venues in total, Saddlebrook being one. So if you'd like to learn about some of the other series that are being offered and the themes and the dates and times, by all means pick this up. We have many copies outside. And in addition, we partnered with the Geosciences department, so we have, you know, the best of the best as far as public speaking that volunteered to be part of this series. So if you want to learn a little bit more about the Geosciences department, and we're typically in the top 5 in the country, if not #1, and our Dean, Joaquin Ruiz, is a geoscientist himself, so it's a powerhouse. But there's a nice brochure about the Geosciences department and some great profile stories of graduate students and others, just to learn about the great work that they're doing. And then many of you know we have Biosphere right in your backyard here, so by all means check out the brochure, and there's a nice coupon on the back, makes it a little easier to digest that admission price. And how many, by a show of hands, have been out to the Mount Lemmon Sky Center? Up on top of Mount Lemmon, right? So do know that we have brochures out there in case you have some guests in town and want to take them up. They just keep adding nice amendments to that. And how many have been down to the new full dome 3D dome projection system in Flandreau Science Center? And don't miss Spooktacular. That's coming up, and that's very family friendly, and they have the chemistry students, and they do very fun science experiments and demos, and they do really fun dome shows that are related to Halloween. But they also have the new Black Hole, and again, this is IMAX quality movies on a 3D dome projection system. And there's a National Geographic version to its Microscopic World, etc. So you want to check out Flandreau Science Center. And how many have been to the Mirror Lab? Excellent. Guess what? Soon, early November, they're casting a new mirror. So we have many in production right now, but there's going to be a new one spinning. And there's nothing like seeing those mirrors in production and multiple mirrors. So keep that in mind if you have guests over the holidays. Well, let me just kind of kick off this series. As I mentioned, our series is Earth's Core to the Clouds. We'll have 3 talks this fall and then 3 talks in the spring, so it'll be a year series. I also want to extend a thank you to the Desert View Performing Arts staff, Darby and her crew, that helped make this happen. Just so you know, the College of Science receives no funding, neither does the Desert View Performing Arts. This is just a community partnership. So thanks for making this a vibrant community partnership. Yeah, it's great. I would like to, in essence, how many have been to one of our Science Cafe series in this venue? Awesome. So we have old friends in this room. And so you know the format, basically about a 45-minute or so presentation, and then room for question and answer. Myself and Samantha, who you might have met out at the table, will roam the crowd with some of the microphones. I'll just ask a favor that you pose your question and then pass us back the microphone so we can have multiple questions from the audience. I know how tempting it is to keep a conversation going with the speaker. And Susan has agreed to stay after if you'd like a little bit of one-on-one opportunity to ask a few questions. We'll be mindful of her time. I know it kind of get late with that long line of questions, but she's offered to do that. and we love your interest. We also, if you didn't pick one up, we have evaluation forms also on the table out front. After you fill that out, please do return it to us. We definitely take your feedback seriously. We share your feedback with our speaker. They love to get the feedback and knowing how to improve or what really resonated with the audience. And also there's a place where you can give us feedback of what kind of topics or themes you would like to have presented during one of these series. And this series is in direct response to one of you that said, I'd like to see some more on geosciences. So here we are. We definitely want to bring what we have that interests you. And I'll also mention there is a place to put, it's an anonymous evaluation. There is a place to put your email address. If you want to receive, we send out a monthly announcement, just a reminder about the talk, if you'd like to receive that. And also the College of Science itself, how many of you have been to the lecture series or watched it online? Yeah, that is an amazing, it's actually going to be on artificial intelligence this year. So that's hosted in Centennial Hall on campus, but it is also simulcast. So Arizona Public Media basically simulcasts that and then records it. So you can actually click on the website after the presentation. So we have all 10 years stored there. Anyway, just wanted to, without further ado, let me go ahead and introduce Susan. The title of her talk, as you can see, Subduction, Earthquakes, and Volcanoes, How They Shape Our Dynamic Planet. We have Susan Beck. She's a professor of the UA Geosciences Department. She received her PhD from the University of Utah and she got her undergraduate degree from the University of Utah and her PhD from the University of Michigan. Any Michiganites out there? Woo! Of course there are. She's been at the U of A since 1990 and does research on subduction zones, earthquakes, and mountain building, especially in the Andes of South America. Not a bad gig to go over there. She also works in Turkey and the subduction related to the Mediterranean. And I did ask her to share a little personal anecdotes about herself, and she loves doing field work in remote regions and traveling to regions after a devastating earthquake to collect the much needed seismic data. I'll come up after the talk, just to remind you of how we'll do the question and answer and then announce next month's talk. Also, there is a flyer on the table for next month's talk. Okay, Susan.
Well, thank you very much. How's the sound? Great. Okay. Well, I'm really pleased to be here, and thank you so much for the invitation. And we do have a fantastic Department of Geosciences. I love it because basically we can follow our passions. We've got great students, graduate students and undergrad students and colleagues. And as you just heard, we have a great dean who's a geochemist. I'm a geophysicist, so I give him a little slack for being a geochemist, but not too much. But I work on earthquakes and mountains and subduction, and I just want to share with you some of the things that are going on that I'm excited about, some of the new things we're learning, and then just a little bit about my research. So I bet a lot of you know a bit about geology, and I'll just start with earthquakes of the world. This shows all the earthquakes of the world for a couple of, I think my pointer's a little weak, for a few decades, and all red earthquakes are pretty shallow, and then the blues and greens get a little deeper. And what you notice is that they're not uniformly distributed, they're concentrated along zones, and those are plate boundaries. The surface of the earth is broken up into plates that are sort of semi-rigid, that move around. We call them lithospheric plates, and they move around on rock that's a little softer, a little more, deforms a little easier, flows over very, very long time scales. And the plates move a few centimeters a year in most cases. So we've known for a long time that these earthquakes are boundaries where there's plates. And we've also noticed that there's what's often called in the public the ring of fire, and around the Pacific Ocean, there's all these plate boundaries where one plate goes beneath another, and that's a subduction zone. And you can sort of identify them because not only do they have earthquakes, but all these red dots are volcanoes. And these are some of the most dramatic and deadly volcanoes in the world. And all these red dots are active volcanoes. So here's a picture of Mount Pinatubo that erupted in 1991 in the Philippines. The subduction zones are also the sites of the biggest earthquakes. And I mean, by the biggest, I mean the magnitude 8s and magnitude 9 earthquakes, the kind we don't see very often. And they often are deadly by themselves, but they produce big tsunamis. And we all saw that in Japan in 2011, where there was a huge tsunami. And it's often the tsunamis that do a lot of damage. And all of these things, the volcanoes, the earthquakes, are all related to this process called subduction. So what it is, if you look in a cross-section, is there's often one plate dives down beneath another plate, and it's often the plate that's more dense, because it's all driven by gravity. Most things on Earth are driven by gravity. So this plate that's often called oceanic plate goes down underneath. It's more dense than this overriding continental plate. So this might be the Andes in Chile. Here's the volcanoes associated with, here's the coastal valley where they grow all that great wine. They get great wine because they get all the ash from the volcanoes, makes great soil. So everybody moves there, and it's a great place to live until the next eruption. And then, of course, the coast is great to hang out on and live. And we all, know people that live on coasts all around the Pacific, but many of them are sitting right on subduction zones. So when the next earthquake happens, all this water is likely going to go produce a tsunami. Now, the big earthquakes I'm talking about, the magnitude 9s, they occur right here between the plates. They're locked up for many, many years, and then as these plates are continually moving due to gravity, pretty soon they overcome the friction on this boundary where they're locked up, and it slips. So these are really important regions to try to understand. So let's just start with the earthquakes, and then we'll go to how we image subduction zones, and then we'll go to volcanoes. So if you look at earthquakes from 1900 to 2011 versus magnitude, here's magnitude 8, here's magnitude 9. We have earthquakes all the time worldwide. They're not periodic, but every once in a while we get some big ones. So 1952, 1960, 1964, we got these 3 big magnitude 9, or in the case of Chile, 9.5, the largest earthquake ever recorded. And then we had a lull. I got my PhD right in here, and I worked on some of these big earthquakes for my PhD. And then I graduate, and oh my God, there's no earthquakes bigger than an 8. And I had to sort of think about what to do. What am I going to do now? But University of Arizona still hired me. I don't think they knew that there weren't earthquakes happening and that I'd have to do something different. But that's okay. That's a great thing about academics. You can follow your passions, and I found plenty more things to do. And then come along to 2004 in December. Do you remember that? That big Sumatra earthquake that killed 280,000 people in Indonesia. I don't know about you guys, but I remember exactly what I was doing the morning when I heard that earthquake happened. And it was just a punch in my stomach, because I knew what that meant, even before the death toll came out. And then in 2010, in Chile, there was an 8.8. I was part of the US response team to go down after that earthquake to put out instruments and record aftershocks and respond to that. And then the 2011 Japan earthquake happened. And we think of Japan as being one of the most prepared places on Earth for earthquakes. They have them all the time. And they're very prepared. But as we've learned with all of these earthquakes, there's always some surprises. I'm going to talk a little bit about the Japan earthquake, because I think there's some real lessons to be learned for all of us from that earthquake. Okay, so what about the death toll? Well, you might think bigger the earthquake, the bigger the death toll, and that's not always correct. Probably hard to read, but this is earthquake magnitude increasing. Here's 9, and here's the death toll, and this is a log scale. And so if you look at the biggest earthquake, the Alaska earthquake, the Japan earthquake, Chile 2010, the death toll for these were, less than 1,000 in 2010, and in Japan, a few tens of thousands. But look up here, the Haiti earthquake 2010 that happened just weeks or a month before the Chile earthquake killed over 200,000 people. And that was only a magnitude 7. So of course it really depends on the population density, depends on the building construction, and really how prepared people are for the earthquake. You can do a lot to be prepared. But the largest earthquakes, all of these 8s and 9s, all occur in subduction zones. And as bad as the shaking is, it's the tsunami that's really, really deadly. So let's talk about the 2011 Japan earthquake. As I said, we think of Japan being prepared, the Pacific plates diving down under, subducting, and here's where the earthquake happened. There was a slit between this overriding plate and the downgoing plate. And these little circles are earthquakes that happen all the time that sort of define this downgoing plate, because it's cold and dense, and so it can break brittly. And all these blue circles in here are aftershocks. Here's where the earthquake initiated, and this is sort of the length of the area that ruptured during the earthquake. It's a fault. It's about 500 kilometers long. And of course, we've known for a long time the Pacific plate's moving this way relative to Japan. And they have very good instrumentation, and so we can really see what happened in this big earthquake. Well, the first thing you might ask is, how strong was the ground motion? That's the first thing, if you're living along the coast, that you want to know. How strong was the ground motion, and it can be used for improving buildings and things. And usually ground motion for strong shaking in close is measured by ground acceleration. Not just moving up and down, but accelerating. And that's not a good thing. Accelerations are measured by 1G, that's the force of gravity. So if you exceed 1G, if we had an earthquake right now that exceeded 1G, we'd all be thrown up out of our seats or into the air. It's greater than gravity. And that doesn't happen very often. There's only a few earthquakes we've recorded more than 1G for. Now, maybe we haven't got the instruments in the right place, but it's not that common. But here's a record of acceleration versus time. That's 200 seconds. And right here, it recorded 2.7 G, almost 3 times gravity. So that was bad. Now, did the ground move in Tucson? Well, now that I put this up, you probably say yes. And it did. Did anybody feel it? No, it's such a small motion, you wouldn't have felt it. But we have a state-of-the-art seismic station out in the Catalina Mountains. And this is time, 8,000 seconds. This is ground motion. Here's the first arriving P wave. It happened 12 minutes. It arrived here 12 minutes after the earthquake started. It took 12 minutes for that seismic wave to propagate through the earth. So if you're paying attention, you would have known the earthquake had already happened. And then we get a secondary S wave, and we get some big surface waves. These surface waves are the undulating things that you might see if you're close to an earthquake afterwards. When the highway rolls, people talk about that rolling motion. Or I felt that rolling motion in California with some earthquakes. If you feel an earthquake and you sit down, get under a table, whatever, you'll get a sharp P wave, a stronger S wave, but maybe not quite as sharp, and then you'll get that rolling motion. And then you'll get other rolling motions back here. So the ground definitely moved in Tucson, and it moved for a long time. This is now 10 hours, and each one of these peaks are different surface waves that continue to move. And what's so amazing to me is what we call R1. That goes from the earthquake around the surface to Tucson, the direct path, the fastest one. R2 goes the other direction, goes a little further. R3 goes around past the station. It's really R1 going around the earth again. So all of these go around the earth multiple times, like 3 or 4 times, and they're still big enough to see. The more times they go around the earth, the more they lose energy and attenuate out. So this is truly a big earthquake when you can see that many times that the seismic wave goes around the earth, and it's still well recorded. Okay, but let's go back to Japan. It didn't do any damage here, and I might have been the only one excited about it, seeing the recording. But how did the ground move? This earthquake lasted about 3 minutes. How did the ground move? 3 or 4 minutes? Well, there was all these GPS stations on Japan, and these black arrows show that Japan moved about 4 meters to the east. That's permanent motion. It's not going back. And these red arrows, which are kind of hard to see, I'm sure, but they point down. So along the coast, the vertical motion was down. That's not good, because that's right along the coast. Tsunami comes in, the ground goes down, makes it even worse, right? You hope things might go up, and that would save you. But that was about 1 meter of subsidence. So what about out offshore where the earthquake was? Well, Japan has GPS stations on the seafloor, which is really pretty rare, and it's very expensive. And they found that these stations, this one right near the epicenter, it went east 24 meters in just 3 or 4 minutes. That's unbelievable. We've never measured anything like that before, seen that. And out here, all these arrows point up, and it went up 3 meters. Remember, on the coast, it went down 1 meter. So here we've got this big horizontal motion along the fault, and we've got a modest, actually I'd say a pretty good vertical motion. Some places go down, some places go up. So what's going on? Well, the idea is that when you've got one plate going down, in between big earthquakes, it's locked right there. And so as the plates are still moving, it shortens this, and you start to get uplift along the coast. So this might happen for 100 years, 200 years. What happens is everybody buys beachfront property or starts planting their rice or doing whatever they're going to do on this nice beachfront. And then when the earthquake happens, which we call coseismic, in those 3 or 4 minutes, it slips here, this pushes up, and you get uplift right out here, but right here, which is often the coastline, you get subsidence. And then the cycle starts over again. And this starts to go up very, very slowly, you know, might be a millimeter a year, might be less, for 100, 200, 300 years until the next big earthquake. And so this area is not where you want to be investing in a lot of infrastructure, because you know it's going to be a danger. And we've seen this with other earthquakes, but Japan is by far the best example. It takes a big earthquake for this to happen. So what you see, and we really saw it also with the Sumatra earthquake in 2004, is that before, you know, this is a bay, this is all buildings and commercial property, and afterwards, of course, it's all devastated, but there's water much further inland that's not going away. So some of this land will be habitable for the foreseeable future. In Sumatra, it really wiped out a lot of rice fields and places where people made their living. And in this case, 75% of the homes were destroyed. And of course, a lot of this destruction was from the big tsunami. So when the earthquake slipped from the seismic waves, we can map out what the slip looked like. And people at UC Santa Barbara did this very quickly, and I'm just showing one of their examples, but many, many researchers did it. And this is where the earthquake happened, this blue box. And red is the highest slip region, which goes up to 55 meters. And then the blues go down, you know, this is 30 meters, the light blue is 15 meters. I always have to look at this and say, are we sure we're talking meters? 55 meters in 3 to 4 minutes. That is huge. It's by far the largest slip we've actually been able to measure. It may have been this big in the 1960 Chilean earthquake, but the seismic data wasn't very good, and so we don't really know. We know it was more than 20 meters. And we used to say, if you get 20 meters of slip, you know, we're in trouble. Well, here we've got 55 meters, and of course we were in trouble. So it's spatially very non-uniform. Some of these places out here, this only slipped 5 meters. It's also not very uniform in time, and in addition to rupturing sort of in and out of the board, it started here, then it ruptured down dip under Japan, and then it slipped up here, and this is what generates a tsunami. When you have slip up here and it offsets the sea floor, it's going to produce a tsunami wave. If an earthquake fault doesn't break the surface or get close to the sea floor, it can't generate a tsunami. So if it's a deep earthquake, you don't need to worry. So tsunamis are certainly a big concern. And how do tsunamis work? Well, the plates are moving, but it's locked right here, and it'll turn red here in a minute. That's building up, and pretty soon it slips and offsets the seafloor and sends out a wave. And this is for just a point source, but imagine that it did this for 500 kilometers. And notice that there's multiple waves, and they propagate out. And think about those waves being 20 meters high. That's pretty hard to defend against. And these are not like surfing waves, wind waves. When you get wind, it sets up waves in the top layer of the ocean, and they break, and you know, people like to surf in them. But a tsunami wave is, because it breaks at the seafloor, it's pushing a whole column of water up. And the other really deadly thing about tsunamis is that when you're in the open ocean, there's long wavelength tsunami waves, and you don't really notice them too much. If you're out in a boat, it's just a big swell. So if you're in the open ocean and there's an earthquake or tsunami coming, stay put. You get in trouble when you go to the coast, because as the water depth shallows, the energy stays the same, and so you get bigger and bigger amplitudes. And how the coastline shallows and the shape of the bay makes a big difference in how big that tsunami is going to be. So it's very different than a wind wave. You don't want to go surfing on it. Here's a little animation that I like that really kind of shows that. So there's multiple waves, and sometimes the wave goes out first, depending on where you're at relative to the earthquake. It did this in the Sumatra 2004 earthquake. People went down and saw all the dead fish, and then they saw the wave come in. And so one of the things you want to know, if you live on the coast where there's a subduction zone, if the water goes out like that, get to high ground, even if you didn't feel the earthquake. And then it comes back in and out, and it may take 10, 15 minutes between going in and out, but it's going to continue for quite some time. So here's a photo that was all over the internet after the Japan earthquake, the tsunami coming in. And you can see this row here. This was a big tsunami wall. So the Japanese did their homework and they said, okay, we should design for a magnitude 8 earthquake off the coast. And we need about a 6-meter wall for that, 5.7 maybe they made it. And they built at a huge expense this big wall. And of course this tsunami came right over it, no problem, because it was not a magnitude 8 earthquake. It was a magnitude 9 that had that 50 meters of slip instead of 10 meters of slip that a magnitude 8 might have. And so this is, you know, really what was bad. Now, a lot of people knew the tsunami was coming. There was some warning. But if you can't get to high ground, you could be in trouble. They have vertical evacuations where they have buildings that are built, and a lot of people went to the top floor of the buildings. So the tsunami gets generated out here in the open ocean, or in offshore where the earthquake starts, and this is 30 seconds after the earthquake happened, and it's going to go rolling in this little animation. And if you're quick, you can see this time. It'll go for about 3 hours, but of course it's going to go super fast. And I wanted to show it because it sort of shows the waves coming in and out. You're at 35 minutes, not quite an hour, now an hour, but look at how the waves are just, whoops. See if I stopped it. The waves are going up and down with variable amplitude, the waves coming in and out. And it's about 3 hours that they're hitting. And why are they so uneven? Well, it's because the energy gets focused or defocused depending on what the bathymetry looks like, or if you're in a cove or an outlet or something. And this tsunami goes up the rivers quite a ways, sometimes kilometers if it's shallow. And so this can be predicted reasonably well, but still you've got to get to high ground and out of there. In this case, most of those waves took about 15 minutes from when the earthquake happened to when they hit the coast. So there was a warning. The Japanese have a very good tsunami warning. People had about 15 minutes to get out. Doesn't sound like much to me, but it's better than nothing, right? So the tsunami also propagated across the Pacific Ocean and made it to Hawaii in about 7 or 8 hours, made it to the West Coast in about 10 to 12 hours. So we had a lot of warning, and we're pretty good at predicting when they're going to hit. Now, they were just a meter or so high. They weren't very high in Western US or South America, but this tsunami propagated all around the world. So why was this such a surprise? Why was Japan not prepared when they really have some of the best seismologists, some of the best instrumentation? And it was because they fell into the trap that we all do. They looked at the last 100 years and saw all these circles with years in them were the last earthquakes. The purple is the 2011 earthquake. And then they went back another 100 years and another 100 years. And it wasn't until and so then they said, well, we haven't seen in, you know, nearly 1,000 years anything bigger than a magnitude 8, so I think we're safe building the wall, the tsunami wall. And about 1,000 years ago, there's evidence of a tsunami that was just as big as this. So these magnitude 9s don't happen very often. And the other lesson that I think we all know is that you can get different size events on the same plate boundary through time. And with each of these earthquakes now, we're learning so much more, and of course it's a little bit scary, but I think the lesson here is you need to make sure you know what the largest earthquake possible is. Then you can decide as a community or a society if you want to design and prepare for that, or you just say it's too expensive, let's hope it doesn't happen for 1,000 years. So I have to say just a little bit about the nuclear power plants, because this, of course, was one of the major disasters here, in addition to the loss of life. And of course, nuclear power plants need water to cool it, and so you tend to want to put them near the coast. And they had backup generators. They designed it for the shaking for more than a G. It withstood all the shaking quite well, but they just didn't expect a big tsunami. And so it took out the power system, then it took out the backup generators. And so then they had no way to cool the reactors, and we know what happened after that. It took about 30 minutes for the tsunami to flood all the control buildings. So I think, you know, this has been a good lesson for all of us. in thinking about safety. Okay, so I want to talk a little bit about, I want to move on to other parts of the subduction zone, and I want to talk a little bit about seismic tomography, because in the early 90s, when there weren't many earthquakes happening, this is what I decided to get into. So what is seismic tomography? Well, we've all had CAT scans, maybe, maybe not, hopefully not. But they put you in this tube, right? And then they've got these X-ray sources, and then they've got receivers, and they just rotate this around and shoot X-rays through you from essentially 360 degrees. Whoops, I gotta stop you screwing that up. Okay. Maybe I have to start it over. Pilot error here. Okay, so seismic tomography is just like a CAT scan. It's the same mathematical equations, except that we have a little bit of a disadvantage. Whereas they can make these X-ray sources any place they want, put the receivers where they want, and in fact spin it around and shoot X-rays through you in 360 degrees. I can't really do that with the Earth. I'd love to. I'd love to put the Earth in one of these machines and do that. And what we know what comes out of this is a three-dimensional image of your head or your body, and it can see differences in density and properties. So, you know, this is a head scan. We get these slices of the brain that we see, and they're pretty amazing. A number of years ago, my mother had a brain tumor, so I saw a lot of these. She's fine, had it removed, and she made a full recovery. But they can really see amazing things. And the same technology works for the Earth. If we could put our sources and receivers everywhere, like they can in a CAT scan. But we can't do that. What are our sources? Our sources are earthquakes. So I can't define where the earthquakes could be. And they're not uniform. They're in subduction zones. And I don't always have a lot of control on where the stations are going to be. But I can try to put out stations or look at where there are seismic stations to collect it. And so the idea is that we can send rays through the Earth, and Earth has different properties, different densities, different seismic velocities, but instead of X-rays, they're seismic rays. So here's a case where I just shoot rays through the Earth from different earthquakes, and these darker areas might be lower density or slower seismic velocity, and if I shoot enough rays, these red regions show up where it slows down the seismic wave, and when it's faster, it speeds it up. So we can come up with these images. Now, they're not nearly as detailed, of course, and the two places that I've been working a lot to try to image are subduction zones in South America and in the Mediterranean, and they're very, very different, and that's why I love working in both places. Today, I'm going to stick to South America. The Mediterranean's perhaps a different talk, but the concept is the same. So I was always interested in mountain ranges and South America and Latin America, and I thought this is where I'll work. And then I found out that there was just a few dozen seismic stations, if that, at the time. And a lot of earthquakes, but there was just no seismic stations like you see in California or Japan. So I started out in the early 90s putting seismic stations in these places. So Bolivia, Peru, Argentina, parts of Bolivia look a lot like southern Arizona and northern Mexico, except right now I'm up at over 4.5 kilometers, or about 15,000 feet in the Andes. This peak goes up to about 19,000 feet. So we're up in the high ground. This is me installing a station with a former graduate student at about 5,000 meters. And what you don't see here is it's on some land with a mine where we got permission. They went up and they're standing by with oxygen, saying, you need to be using oxygen. And we're saying, no, we don't, because we didn't want to mess with it. So what do? For the last 25 years, I get seismic equipment, take it to South America, we test it, we load it up into trucks like this, and we head out and we install seismic stations with crews of students and locals and collaborators. Here's one of the sensors, here's our electronics. We cover it all up. Now, this is National Science Foundation support, your tax dollars at work, but I want to tell you that your tax dollars don't pay for me to send the data back by satellite. That's just way too expensive. So every 4 or 5 months, we'll send a graduate student and we'll go down to each one of these sites and collect the data. And we've done this for hundreds and hundreds of seismic stations over the years. But it's paid off because we can now start to image the region. And I'm just going to show you one example. All these colors are seismic stations, and about 2/3 of them I've been involved in putting out. The other seismic stations were done by different European groups. But all the data is open, and we record earthquakes from all around the world for 2 years. It takes about 2 years to get enough data. 546 earthquakes in this study, but we've gotten thousands of earthquakes overall, recorded in this case at 384 stations. We're now up to about 1,000 stations we're working with. And what do we see? Well, this is work by my former graduate student, Melissa Charay, and we can take depth slices just like you can in the CAT scans, and the blue regions are high seismic velocity and the red are slow. So these are the subducting oceanic slabs or plates going down. Here they are down at 410 kilometers, and we see them all the way down to about 900 to 1,000 kilometers before we lose resolution. And so we've always known that these slabs subduct and go down, but now we can actually image them, and we can say something about their seismic velocities. It might be a little easier to see in cross-section. So here's the Andes, and these are just cross sections 1 through 5. Up here in Peru, that slab comes in and it just goes vertical. We don't understand why it's going so vertical. But then as you come further south, it's dipping at a little bit shallower of an angle, and it's going into what we call the lower mantle. There's a big viscosity contrast. This is much thicker than this, and a lot of times we weren't sure if these slabs could actually penetrate that deep, but we know that they do. And in addition, we're seeing all these other kinds of anomalies, like this blue might be a piece of a remnant slab that broke apart, that's just hanging out there. And some of these red features are slow velocities, and we think that in part that's because they have a lot of water. So there's a lot of thought that there's big oceans down in the mantle in this part of the earth, and there's a lot of water hanging out. And this would be the kind of evidence, because the water would lower the seismic velocity. So here's a 3D image of part of it where you can see the shape, and we see tears, and we see all kinds of different features that we can then begin to interpret. So that's just sort of one example of what we're doing, trying to image subduction zones. And we're doing it now from Colombia all the way down to southern Chile. I want to turn now to volcanoes, because they're a big part of this story. And as we said, we've got the subducting plates going on, and we've got these volcanoes up at the surface, and they're directly related to this, because what happens is if you want to melt the rock that's in this part of the mantle, and I have a piece of it right here. A few of you up close can see this green. That's olivine crystals. Olivine is what the mantle, it's a mineral that's in the mantle that's made up peridotite. Has anybody got an August birthday? Okay, you know what the gemstone is? Yeah, peridot, right? Yeah, it's olivine, basically. Now, that's not gem quality, of course, but I figured it was fate that my birthstone comes from the mantle, and that's what I ended up studying. Of course, I didn't know that for years until I got into college. I just thought it was a nice green stone. But what happens is we've got to melt some stuff to get a volcano, right? Because there's magma that comes up. And one way to melt it, of course, is to add heat. But in this case, we're subducting this cold, dense plate. So we're cooling off this part of the mantle. We're not heating it up. So what happens? Well, when we subduct it, the material in the oceanic crust dehydrates. It gives off water. And that water comes up and melts this. So if you take this peridotite and you add water to it, you don't change the temperature or pressure, it'll melt with water, whereas if you don't have water and it's dry, it won't melt. So that water is key, and you've got to have the subduction to get the water. So the water comes up, it melts the mantle rock, these peridotites, they go up to the base of the crust and into the crust, and somehow mix with these crustal rocks that are more like granites, more like what we see here in the Catalinas. And then they mix, we don't know what happens to them exactly, where they hang out, and then they make their way up to about 5 kilometers from the surface before they erupt. So So these kinds of volcanoes are called stratovolcanoes, and they have that nice cone shape. That's Sajama in Bolivia. It hasn't erupted in quite a while. Here's Mount Rainier. It hasn't erupted really in quite a while. It had a little bit of smoke and vents in the late 1890s. This is the Philippines, Mount Pinatubo, and this is Mount St. Helens. Now these kinds of big eruptions, and this is a big lahar and ash flow, they go about 60 miles an hour. You can't outrun them. If you're not out of the way by then, that's pretty much it. So they're quite deadly. And it should worry you a little bit seeing pictures like this and looking at where everybody lives now at the base of Mount Rainier. So what happens? Well, we get this water that comes up and we form these, we know we form some kind of shallow magma chamber at shallow depths. These usually aren't very big and they might be just a few kilometers deep and fills with gas. It has a lot of dissolved gas, and as it comes up through the crust, the gas gets released and it gets very, that builds up a lot of pressure, and when it finally blows out, it's very eruptive. It has a lot of silica in it. That makes it really viscous and thick, so, you know, when it erupts, it splatters all over the place and is very, very deadly. But this is just the very shallow part. So what happens further down? This is the mantle where we bring up all that, melt all that olivine, gets in here and mixes somehow, and then makes it up to the surface. And what we're trying to image is all this region in here, which schematically just shows some fractures or something going up. And it really doesn't look like that. So we want to know a little more about the path it takes from down here at depths of 70 to 100 kilometers up into the 20, 30, 15 kilometer range. And we can do that with seismic tomography on a little different scale. So once again, we're looking at the Andes, and these red triangles are all the active volcanoes. So you get active volcanoes from up here in Peru all the way down to southern Chile, and of course you get more up in Colombia and Ecuador as well. And so we can image this with seismic tomography, and I want to talk about two regions in what's called the Puna Plateau, which is right here, the Altiplano-Puna Volcanic Complex and Cerro Galán. The Puna is a big plateau that's about 4 to 5 kilometers high, and it's nothing, you feel like you're on the moon. There's very little vegetation, and it's just volcanic. It's also where there's the pink flamingos, if you ever see those pictures of a volcano with a pink flamingo. So this is a blow up of that region. This is all high topography, and we can get seismic images, and these are cross sections. One goes across here, one goes a lot here. They go from 0 to 80 kilometers depth, and they go several hundred kilometers across here. And the scale is that white is extremely low shear wave velocity, and the blues are pretty fast shear wave velocities, and the greens and yellows are in between. So up here in the Altiplano volcanic complex, we see this white that has shear velocities as low as about below 2 kilometers per second. That's really low in the crust, and it means that there's probably about 20% partial melt. If it's 100% partial melt or 100% melt, S waves won't propagate through it at all. But these are some of the lowest seismic velocities imaged anywhere in the world. And look at this big horizontal magma body. It's 150 kilometers across. It's at about 15 to 20 kilometers depth. And it's way bigger than one little volcano. It covers a huge area. In fact, it covers this area with the dashed line. We've mapped it out at depth. If we go a little further south, they're a lot smaller bodies, and they're not quite as low velocity. Here's one right here under Cerro Galán, a very active volcano that's here. Here's another one a little deeper. Looks a little bit different, but we think that this one is building up and may someday look like the one to the north. Well, right above it is this little peak, Erupt. That's what it looks like. This is what the Puna looks like, very little vegetation. This thing is way bigger. All of these peaks that are white, those are little, you know, high elevations above about 3 kilometers high. So what we're seeing is that there's not just little bitty magma bodies under each volcano. And when I say little bitty, when I'm out here, that doesn't look so itty bitty. but it's small compared to the size of this magma body that has a 20% partial melt. So it's huge. And you know, we used to go out and see the surface volcanic rocks like basalts and andesites and say, well, we know they came from a magma chamber, and it was probably a ratio of about 1 part extrusive volcanic rocks and 3 or 4 parts magma, partial melt magma body. Now we know this volume gives us a ratio of 1 to 25. This is the kind of thing that probably used to be below Yellowstone. Something like this before it had the massive supervolcano caldera eruption back 500,000–600,000 years ago. But this is by far the largest crustal magma body that's ever been imaged anywhere in the world, much bigger than Yellowstone. And you know, I know you go to the web and you see, oh, we've imaged the largest magma body ever under Yellowstone. That's not true. They're not reading our papers. But nonetheless, Yellowstone is big. But we're seeing that our picture of just these vertical fracture-like bodies is not correct. Okay, I'm going to wrap up here in a few minutes, but I always get asked the question, could we have subductions on earthquakes in the US? And the answer, of course, is yes. We had the 1964 Alaska earthquake, but closer to home is the Pacific Northwest, and we have a subduction zone off the coast of Oregon, Northern California, Oregon, and Washington, and southern Canada, and Vancouver. And so there's a plate subducting down beneath here. We've got the volcanoes, Mount St. Helens, Mount Rainier, Mount Baker, all of those are active volcanoes. The plates are moving very slowly, and there's been a few earthquakes in this region. I can think of one in 1967 and another one in early 80s, but they were really small, and they were in the plates and, you know, shook Seattle a bit, wasn't a big deal. But we know there was a big one in the year 1700. And that's what is worrisome. So why do we think that? Well, we think that because on January 26, 1700, some Japanese seismologists went back and looked at old records written in a Japanese language, but I guess an older language, and it described a big tsunami that hit Japan. And the way it hit Japan, they could tell it came from the Pacific Northwest. So we have almost a time and a date for this big earthquake. And it looks like this whole region in blue slipped in a big earthquake that might have been close to a magnitude 9. Now, we can't be sure. Maybe it was an 8.5 and it just produced a big tsunami that made it to Japan. 300 years ago or so, 1700, this area wasn't settled. There's no written record. There's a lot of Indian legends about canoes being left in treetops and things. But this is the worrisome. This would be the next big one for the Pacific Northwest. Now, maybe it'll break in 3 magnitude 8s. That wouldn't be quite as bad as a magnitude 9, even though there'd be 3 of them. So this is the thing that if you live in the Pacific Northwest, you're concerned about. A year or 2 ago, there was a really nice article in the New Yorker that described all of this and what could happen. And the main thing is if you're on the coast and you feel the shaking or you hear a siren, that means a tsunami is coming, get to high ground. The other evidence for this, which I think is kind of neat, is Brian Atwater, a geologist at the USGS and the University of Washington, was mapping along the coast and noticed that when he dug down, there were these sort of peat layers of plants that didn't live in the intertidal zone, but now were in the intertidal zone. So the idea is they were plants that when that big earthquake happened and there was subsidence along the coast, they got buried by a meteor or 2. So they're freshwater plants that couldn't live in this sort of salty seawater tidal zone. And then you also see areas like this with these big cypress trees and things that are dead, that are still standing. And again, they're down in this sort of area that has partial salt water, and they could never grow at that right at sea level. So again, they've been inundated with seawater and it's killed them. And I was fortunate to go on a field trip with Brian a number of years ago to see all these kinds of things. And these can't be big storms because it happened suddenly. The trees all died at once. So we think this is evidence of that subsidence that we've now measured in Japan that happened. And when you carbon date these, it comes out to be around 1700 plus or minus maybe 20 years. So we can't be sure with the carbon dating, but it happened at some point. So yes, we have two regions where we can have these kinds of big earthquakes, Alaska and the Pacific Northwest. The volcanic eruptions. Well, we know we can have those because in 1980, Mount St. Helens blew, one of the Cascade volcanoes. Again, do you remember where you were in 1980 when that happened? I sure do. I was a graduate student, and it was a big deal. It sort of woke me up that, oh my gosh, we got big volcanoes. Before that, they were just great mountains that I used to like to climb. I used to like to go out to Mount Shasta and ski down it. And I was, very excited about that. And I knew it was a volcano, but, somehow knowing it's a volcano and then seeing Mount St. Helens erupt was two different things. On the left is the Mount St. Helens before it erupted. Of course, it all blew out. Some of it blew out the side, killed some people, but it wasn't very populated. Unlike Mount Rainier, which is now considered one of the deadliest volcanoes on Earth, because people have built up at the base of the volcano, there's a lot of communities, and they're on these big lahar, these big ash deposits that came rolling down the volcano. And of course, again, it's good soil, and it makes these beautiful river valleys. So there's a lot of people at risk. Now, the good thing about volcanoes is we can see eruptions coming and predict them a lot better than earthquakes. Often there's a lot of earthquakes that start, there's some doming, there's a fair amount of indication. Earthquakes, we still have no way to predict. So I'll stop there, and hopefully you'll realize subduction zones are pretty interesting places. Thank you.
So as I mentioned, Samantha and I will just get on either side and we'll take questions. I see the first one over here and second one there, Sam.
The large Puma magma chamber, is that going to erupt like the Yellowstone?
Eventually it could. It erupted, had some big eruptions between about 3 and 10 million years ago, but it looks like it's still accumulating. I don't think it's going to be in our lifetime or anything, but eventually it is going to blow out. All that magma and that's down at 15 to 20 kilometers is going to make its way to the surface, probably. But we may still be looking at thousands of years, and it's not very populated, although you'd certainly know about it because, of course, it would put ash in the air that would circle the globe.
The recent earthquake in Mexico, would that have any effect on like the San Andreas Fault or any of the other faults up in Southern California?
Yeah, good question. Probably not. The earthquakes in Mexico, both the 8.1 and 7.1, didn't occur between plates. They occurred in the subduction zone, but in the downgoing plate. And so that downgoing plate's not really connected to the San Andreas. They're on different plates. So I think it's unlikely that there would be any direct connection. But it still reminds us that earthquakes sort of cluster. In Japan, when the 8.1 happened, people sort of thought, well, great, it wasn't quite as bad as we thought. And then the 7.1 got, was much closer to being under Mexico City. Now, the interesting thing about Mexico City, maybe some of you know, it's built on old lake bed sediments. And so those sediments are softer and they amplify the seismic waves. So they're much stronger than they would be if you were sitting on hard rock somewhere. So you're always better off when there's an earthquake if you're on hard rock rather than on soft sediments.
Does climate change have any impact on volcanic activity or earthquakes?
Oh, great question. You're putting me on the spot here. Let me turn it around and first say that the big volcanic eruptions do put a lot of CO2 in the air short term, and they can impact the climate for months to years. The 1991 Pinatubo eruption affected the climate for about a year. But if you turn it around, I would say there's no good evidence for that. There are theories that the hurricanes triggered the earthquakes in Mexico, right? Because we had 3 hurricanes in a row that happened, you know, right before, there was a hurricane right before each. So the idea is that the hurricane changes in pressure would couple to the ground somehow and stress things. But there's no real physical mechanism for that, and seeing 2 events that happen close in time doesn't give you cause and effect. So I would say I don't think there's any evidence for that, but of course people will be watching. And if you go back in time, there's many, many hurricanes that never trigger an earthquake. So I would have to say that in general, there's not a direct connection.
Talking about soft sediments, isn't the Oro Valley a several thousand foot deep sedimentary valley that we built all these houses on top of? And does that make them vulnerable if an earthquake?
Yeah, so the Tucson Basin and Oro Valley, we're sitting on sediments. So it is a little bit of a concern, but they're not as soft to sediments as Mexico City or Salt Lake City, because those used to be big lake beds. But the shaking in the Tucson Basin and Oro Valley would be much different than if you're up on the Catalina bedrock or in the Tucson Mountains. Now, the good thing is we don't have a lot of earthquakes here. We have a few up in Arizona. We have a few up near the Grand Canyon. We had one a few years ago near New Mexico. But they're usually magnitude 4s, maybe a 5. The biggest earthquake that was felt in Tucson was in the late 1800s in northern Mexico, just south of Douglas, on the Patachi Fault. And there's a big fault scarp down there you can still see. And it happened in northern Mexico, but if you lived in Tucson, you felt it. If you've been out to the San Javier Mission, in their museum, they have pictures of those bell towers that cracked and fell down during that earthquake. And of course, they've been repaired. So if that happened again, of course, now Tucson is built up and it would be a bigger hazard. But in general, those faults look like they have recurrence intervals of tens of thousands of years. So I would never say there cannot be an earthquake here, but earthquakes are pretty rare here. But it's true, if you were living in the basin, you'd have more shaking than on the bedrock. You know, of course, we all know our biggest hazard is probably flooding.
Yes, I have a question on the seismic tomography. So the waves that you're reading, are you generating them like through a sparker or something like that? Or are you just reading the intrinsic waves that are generated? They're generated by earthquakes.
The earthquakes are our sources. Okay. And if you tried to use, you know, dynamite or some man-made source, you would never get it to propagate down to, you know, 1,000 kilometers. So you have to use earthquakes. And that's why we have to wait 2 years to record thousands of earthquakes to do this. But if you're patient, it works.
How does climate change, glaciers melting, sea levels rising, affect or influence the effect of tsunamis?
Well, there's going to be a couple speakers that know more about climate than I do, but it's a huge impact on tsunamis, right? Because sea level's rising. So suddenly your water is a meter or 2 higher than it was, so that means your tsunami that's 10 or 20 meters above sea level is going to go that much further inland and be that much worse. So the combination of these big earthquakes happening along the coast of South America, the Pacific Northwest, and sea level rise is going to make it a lot worse.
During an earthquake, sometimes there seems to be lights coming in the sky. Do they precede the seismic activity?
Those lights are interesting. I personally haven't seen them. And I've been in a lot of earthquakes. I've seen pictures. I wish I could see them. They generally don't precede earthquakes. There's a lot of things that people measure, hoping that they will tell you an earthquake is coming. And the problem is, we always look at them in hindsight, and they're always different. In 1989 in California, the Loma Prieta earthquake, there was some electrical activity right before the earthquake. But then as they look back to previous earthquakes, it didn't happen. So this idea that we're going to find something that always happens before an earthquake, even an earthquake on one particular fault, just hasn't panned out, unfortunately.
Do you get into things where avalanches can cause problems? I'm specifically thinking of
I think it's La Palma Island that's cutting in half, and if that thing goes, it could cause a phenomenal tidal wave that could come right across it.
Which island?
I think it's called La Palma. It's off the coast of Africa.
Yeah, the Canary Islands, yeah. Yeah, oh, no question. Big landslides into the water can generate big tsunamis. In fact, there was a big one up in the Aleutians near Alaska in 1946 that slid, and the tsunami it generated killed people in Hawaii. If you go to that little park near Hilo, there's a monument to all these kids and the names. That was a big landslide. Now, the other thing that happens is an earthquake can trigger a landslide, so you can get a double whammy. In 1970 in Peru, an earthquake triggered a big landslide off a big mountain with snow and glaciers, and it became a big mudslide, and that mudslide killed 65,000 people. It was the most deadly earthquake in South America. And it was not the earthquake, not the tsunami, but it was the big, massive mud landslide that did it. So all these things go hand in hand.
I'm just wondering about the big earthquake that was in New Madrid. That doesn't seem to have any relation to any tectonic plates as far as I know.
No, you're absolutely right. New Madrid is in southern Illinois, Tennessee, that area near St. Louis. And in 1811, 1812, there were a series of 3 earthquakes that might have been around magnitude 7 or 7.8. We didn't really have seismic instruments. And the shaking, the reports are pretty amazing. If you read them, they talk about the Mississippi changing course and flowing backwards. And that's right, that is within a plate. And so the plates are not completely rigid. There's a couple theories about that. One that's probably most thought of is we really don't know why it happened, but it's right where there's an old rift. And that is millions and millions of years ago, the country, it was starting to pull apart. And some basalts came in, and there's a big contrast in the density of the rock there. And so that seems to be where those earthquakes are concentrating. Then there was also big glacial deposits that came down almost that far. As the glaciers were moved back, we see the ground starts to go up and stresses. So it's some combination of things that causes those stresses. But prior to 1811, there's no record of an earthquake. And so if we put out GPS instruments, the motions there are tiny. So the best guess is that these kinds of events are really rare and, you know, probably not going to happen again in thousands of years. But, you know, never say, don't worry, because that part of the country, the Midwest, is very rigid. And so a magnitude 6 earthquake there would shake much harder than a magnitude 6 earthquake in Nevada, because the crust in Nevada, California, Arizona, it's a little softer, it's hotter than in the Midwest. Or remember the Virginia earthquake that damaged the, you know, that wasn't a big earthquake, but it did a fair amount of shaking because the ground is so rigid.
Has there been any research on animal behavior prior to either an earthquake or a volcano observations?
Yeah, a lot of that research has been done in China and in Russia and other places. And back in the late 70s, China was doing a lot of it. And they thought that they could see changes in animal behavior, and they were measuring all kinds of things. And they predicted an earthquake in 1975, and they evacuated 500,000 people, and the earthquake happened within a few days. And it was a huge success, and everybody's saying, wow, finally, someone's figured this out. The next year in 1976, they missed an earthquake, and upwards of 700,000 people were killed. And since then, a lot of people in the US have been tried to look at animals. In the 1970s, we promised the public, we being seismologists, of course I was a kid at that time, that if you just give us enough money, we'll predict earthquakes. Well, that was a bad idea, right? Because what happened is people expected us to predict earthquakes, and you just can't. So I think there's really no credible evidence that we can use. Now, I think some animals do probably sense things, but it's hard to know what they're sensing and whether it's kind of construction going on or something else. Turtles have really sensitive ears and can sense vibrations, so there was a thought maybe they could sense it. Fish start swimming, going crazy. There's all kinds of people out there who will try to tell you we can predict earthquakes. There's a guy in California who watches how many lost dogs there are every day, and if you get enough lost dogs, he predicts an earthquake. Well, there's an earthquake every day. So I can predict an earthquake. There will be an earthquake tomorrow somewhere in the world. There's earthquakes every single day. But you have to be specific about when and where, and in a deterministic way, we just can't do it. After the big damaging earthquake in the late 1999 in Turkey, there was somebody that called me, a lawyer, and said, I've got these clients who are about to pay $50,000 to somebody who says, if you pay me $50,000, I will tell you when the next earthquake in Turkey is going to happen and you can get your family out. And he was targeting Turkish immigrants. Well, my God, you know, $50,000. Yeah, I looked at the website. It was all totally bogus. So, you know, there's all these things out there. And again, you have to be careful what you read on the internet. But we really cannot predict when earthquakes will happen. We know where they're going to happen, on fault zones, in subduction zones, where they've happened in the past usually, but we just can't say when.
We were in New York about 5 or 6 years ago, I think it was, and there was an earthquake. It's the one that in Washington destroyed the top of the Washington Monument and everything. It's awfully populated on the East Coast. Exactly. So what is the likelihood? Is there a fault there? Is there a likelihood that, you know, there could be a problem in evacuating people and prediction?
Yeah, there are faults all over the country, and many of them old. And the question is, are they active? There are small earthquakes in New York State. There's a seismic network in New York State run out of the Lamont Columbia University. But there's no question an earthquake of magnitude 6 near New York City would be pretty devastating because of the way, the population density, the way the buildings are. It's unlikely that it would happen there. I mean, California is going to have much more earthquakes, but you can never say never. The question is, what do? You have to be able to say, what risk am I willing to take and at what cost? To retrofit buildings is incredibly expensive for something that might not happen in your lifetime, 50, 100 years. So it's a real dilemma. I mean, you'd love to say, let's just fix every building in the country and make sure, but the East Coast is a problem. The other thing that's becoming a little more of a problem is induced earthquakes, induced seismicity. Have you heard about that?
Oklahoma.
In Oklahoma, there are days where there are more earthquakes in Oklahoma than California. Who'd have thought? And it's because they're pumping water, fracking water. It's not the fracking itself, but they use water. They take that wastewater and they pump it back into the ground. They don't want to leave it around because it's full of chemicals. And that's inducing earthquakes. And so, and this happens everywhere. And you may think that's bad. Fracking is bad. It's giving us a lot of natural gas and the price is good. But that can be controlled with some work if you do it right. And so if you do a little bit of research, you can figure out what is a safe level to pump in the ground that won't induce earthquakes. And I think we're at the stage where we need to make sure that that kind of thing is happening if we don't want to shut that down.
Yes, in a different direction again. Charleston, South Carolina, passive margin. Do you know what happened there? I've never really read anything about it.
Yeah, so was it 1864, an earthquake? Okay, I got to keep my earthquake straight. Yeah, South Carolina, Charleston. There's a big fracture zone. It's a passive margin, you're right, there's no plate boundary, but as the mid-Atlantic ridge is spreading, the Atlantic Ocean has these big fracture zones, and it's right in line with the fracture zone heading into the continent. So the thought is that it's on that continent, and the passive margin has continental crust, which is not so dense, and oceanic crust that's dense, and there are differences, so there's a little stress there. And often subduction zones start where they have that difference. So that's likely the cause of that earthquake. And again, you know, we don't know how common that is, but it's a transform, yeah, it's a transform fracture zone coming in, Yeah, is the current thinking. But again, it's a little further inland than you might have thought it would be. And so there are a lot of settings for earthquakes.
So why is there a giant volcano at Yellowstone? Is that an old plate boundary, or is that a hot spot like Hawaii? Or?
Yeah, it's more like a hot spot. There's a plume under it that's been imaged. So it's much more like Hawaii. Hawaii's coming up through an oceanic plate, and that plume is bigger in Hawaii and goes all the way down to the core mountain boundary, which is about 2,700 kilometers or so. The Yellowstone plume seems to end at about 700 kilometers, but you can see a low velocity zone, very low seismic velocities, a lot of fluids down to about 700 kilometers beneath Yellowstone. So it's not a plate boundary, but it's a hot spot.
So I know we have many other questions. I don't know if you can detect, but Susan's voice is getting a little raspy. So if you want to grab it, drink water. So I'm going to ask one last question, and then we'll invite folks down. If you'd like to ask questions to Susan, she's decided to stay afterwards. Just a quick announcement about next month. So on Thursday, November 9th, again at 6:30 p.m., we'll have the Earth's Greatest Mountains, the Rise and Demise of Extreme Topography. So as you might guess, these talks literally dovetail with one another, so they build on concepts. I know Susan also has some cool specimens up here. And before we turn it over to one-on-one questions, would you just explain or tell us how you got involved in this field?
Oh, well, yeah.
Especially a woman in this field?
Yeah, good question, I guess. So I grew up in Colorado. My big thing was skiing in the mountains and hiking in the summer and the usual thing you did in Colorado as a kid. And then I went off to the University of Utah because I got a ski scholarship and spent my time skiing. But you had to major in something. And so I moved around. What can you major in where you can miss half the year skiing, right? And then I took a class in geology, and we did all these cool field trips. And I said to myself, you can major in this. You know, you go out and you look for fossils and you climb mountains. You can major in this. You know, there's actually jobs. There's something you can do. So I became a geology major, and I always liked math. And so then as I progressed, well, first of all, I realized, okay, after 4 years, you know, I love to ski, but I wasn't going to make a living at it. So I thought, well, okay, I'll go to graduate school because you got to go to graduate school. And I liked math, and I'd taken a lot of math. So as I was going during geology, I loved it, but I thought, well, you know, here's this fault that's 60 million years old, and here's this fault that's 80 million years old. I'd really like to work on active tectonics, earthquakes, and, you know, active stuff. So that's when I decided to do seismology for my PhD, and you know, never looked back. And I will say that I have been incredibly fortunate because I've been able to do what I love and passion, and I feel like I've never gone to work a day in my life because every day I'm loving it and I'm doing what I want.
Please join with me in thanking Susan again for a great talk. We also have more evaluation forms right down here, and Sam can give those to you, but we'll keep Susan for a few more minutes.